that will reproduce what you see here in the spreadsheet. So how this works is that the over keyword is signaling to SQL that you want to use a window function. And this means that you will get an aggregation, you will do a calculation, but you're not going to alter the structure of the table. You are simply going to take the value and put it in each row. This is what the over keyword signals to SQL. Now, because this is a window function, we also need to define a window. What exactly is a window? A window is the part of the table that each row is able to see. Now, we will understand what this means much more in detail by the end of this lecture, so don't worry about it. But for now, I want to show you that this is the place where we usually specify the window inside these brackets after the over, but we have nothing here. And what this means is that our window for each row is the entire table. So that's pretty simple, right? Each row sees the entire table. So to understand how the window function is working, we always have to think row by row, because the results can always be different on different rows. So let us go row by row and figure out how this window function is working. So now we have the first row, and what is the window in this case? Meaning, what part of the table does this row see? Well, the answer is that this row sees all of the table. Given that it sees all of the table, it has to do the sum of power. And so it will take this thing, compute a sum over it, put it in the cell. Now that was the first row. Moving on to the second row. Now, what's the window here? What part of the table does this row see? Once again, it sees all of the table. Given that it sees all of the table, it takes power, computes sum over it, gets the result, and puts it in the cell. Now, I hope you can see that the result has to be identical in every cell, in every row, in other words, because every row sees the same thing and every row computes the same thing, and this is why every row in here gets the same value. And this is probably the simplest possible use of a window function. So let us now take this code and bring it to BigQuery and make sure that it runs as intended. And like I said in the lecture on grouping, you will see that power is blue because BigQuery is getting confused with its functions. So always best practice to put it into backticks to be very explicit that you are referring to a column. But basically what you see here is exactly what we have in our sheet. And now, of course, we have this new field which shows me the total of power on every row. And like I said, we can use this for several purposes. For example, I can decide to show for each item what percentage of total power it covers, right? That's what I did before in the sheet. So to do this, I can take the power and I can divide by this window expression, which will give me the total power. Not sure what happened there, but let me copy paste here. And I can call this percent total power. Now this is actually just a division, so if I want to see the percentage, I will have to also multiply by 100, but we know how to do this. And once I look at this, we can see that when we have power 100, we have almost 6.5% of the total power. So this is the same thing that we did before. And this goes to show that you can use these fields for your calculations. And like I said, if this was your budget, you could use this to calculate what percentage of your total budget is covered by each item. It's a pretty handy thing to know. Now, why do I have to take this to repeat all of this logic over here? Why can't I just say, give me power divided by some power? Well, as you know from other parts of the course, the select part is not aware of these aliases, it's not aware of these labels that we are providing. So when I try to do this, it won't recognize the label. So unfortunately, if I want to show both, I have to repeat the logic. And of course, I'm not limited to just taking the sum, right? What I have here is an aggregation function, just like the ones we've seen with simple aggregations and grouping and aggregations. So instead of sum, I could use something like average, using the backticks, over, right? I need to remember to add the over, otherwise it won't work because it won't know it's a window function. And I can give it a label. And now for each row, I will see the same value, which is the average of power over the whole dataset. And you can basically use any aggregation function that you need. It will work all the same. Few more backticks to put in here just to be precise. But the result is what we expect. Now let us proceed with our explorations. So I would like now to see the total power for each row, but now I'm not interested in the total power of the dataset. I'm interested in the total power by item type. Okay, so if my item is an armor, I want to see the total power of all armors. If my item is a potion, I want to see the total power of all potions, and so on. Because I want to compare items within their category, I don't want to compare every item with every item. So how can I achieve this in the spreadsheet? Well, let us start with the first row. So I need to check what item type I have. And conveniently, I have sorted this so we can be quicker. Now we have an armor. So I want to see the total power for armor. So what I can do is to get the sum function and be careful to select only rows where the item type is armor. And this is what I get. And then the next step would be to simply copy this value and then fill in all of the rows which are armor, because for all of the rows, but again, you have to be careful because the spreadsheet wants to complete the pattern, but what I want is the exact same number. And then all of the rows that have item type armor will have this value because I'm looking within the item type. Now I will do it for potion. So here I need to get the sum of power for all items that are potions, 239, and then make sure to copy the exact same value and to extend it to all potions. And next we have weapons, so sum of all power by weapon, which is here, then copy it and copy it, and then let's see if it tries to complete the pattern. It does, so I'm just going to go ahead and paste it, and now make this a bit nicer, and now I have what I wanted to get. Each row is showing the total power within the items that are the same as the one that we see in the row. Now, how can I write this in SQL? So let me go ahead and write it here. Now, two parts of this query will be the same because we want to get the items table and see these columns, but we need to change how we write the window function. So once again, I want to get the sum of power, and I will need now to define a specific window. Now remember, the window defines what each row sees. So what do I want each row to see when it takes the sum of power? For example, what do I want the first row to see when it takes the sum of power? I want it to see only rows which have the item type armor. Or in other words, all the rows with the same item type. And I can achieve this in the window function by writing partition by item type, by adding a partition. Defining the window as a partition by item type means that each row will look at its item type and then will partition the table so that it only sees rows which have the same item type. So this row over here will see only these 4 rows, and then you will take the sum of power and then you will put it in the cell. And for this, the second, third, and fourth row, the result will be the same because they will each see this part of the table. When we come to potion, so this row over here will say, hey, what is my item type? It's potion. Okay, then now I will only look at rows that have item type potion, and so this will be the window for these 4 rows. And then in those rows, I'm going to take power and I'm going to sum it. And finally, when we come to these rows over here, so starting with this row, it will look at its item type and say, okay, I have item type weapon. Let me look at all the rows that share the same item type. And so its window will look like this. So let me color it properly. Its window will look like this, and then it will take the sum of these values of power that fit in the window and put it in the cell. Second cell sees the same window, sums over these values of power, puts it in the cell. And this is how we get the required result. This is how we use partitioning in window functions. So let's go now to BigQuery and make sure that this actually works. And when I run this, I didn't put a label, but you can see that I'm basically getting the same result. When I have a weapon, I see a certain value. When I have a potion, I see another one. And when I have an armor, I see the third value. So now for each item, I am seeing the total power, not over the whole table, but within the item type. Now, next task, find the cumulative sum of power, which is this column over here. What is a cumulative sum? It's the sum of the powers of this item plus all of the items that are less powerful. So to do this in the spreadsheet, I will first want to reorder my data because I want to see it simply in order of power. So I will actually take this whole range and I will go to data, sort range, advanced options, and I will say that the data has a header row so that I can see the names of the columns. And then I will order by power, ascending. So as you can see, my records have now been sorted in direction of ascending power. Now, how do I compute the cumulative sum of power? In the first row, all we have is 30, so the sum will be 30. In the second row, I have 40 in this row plus 30 before, so I will have 70. When it comes here, I have 50 in this row, and then the sum up to now was actually 70, which I can see by looking at these 2 cells, or I can see more simply by looking at the last cell. So 50 plus 70 will be 120. And proceeding like this, I could compute the cumulative power over the whole column. Now, for your reference, I have figured out the correct Google Sheets formula that will allow you to compute the cumulative sum of power for our example. And I went ahead and computed it so that we have it for all our data. Now, this is the formula right here, and I'm not going to go in depth into it because this is not a course on spreadsheets, but I will show you the formula just in case you're curious. So the SUMIF function will take the sum over a range but it will only consider values that satisfy a certain logical condition. So the first argument is the range that we want to sum over, and this is the power. And the criterion, so what needs to be true for a value to be considered, is that this value is lesser than or equal to the level of power in this row. So what this formula is saying is take the level of power in this row and then take all the values of power which are lesser or equal and then sum them up. This is exactly what our window function does. And so our formula reproduces this. Now, if you go and look what's the way to do a cumulative sum in Google Sheets, or what's the way to do a running total, there are other solutions, but they do come with some pitfalls. They do come with some corner cases. So this is a formula that's actually reproducing the behavior of SQL. Now let us go back to actually SQL and see how we would write this. So I'm going to take the fantasy items table and I'm still going to select the columns. And now I have to write my window function. Now the aggregation is just the same. So take the sum of power. And now I have to define my window. Now my window is not defined now by a partition, but it is defined by an ordering. Order by power. And when I say order by power in a window function, what's implicit in this is the keyword ask for ascending. So this means that the window will order power from the smallest to the biggest. And I can choose to write this keyword or not, because just like in order by in SQL, when you don't specify it, the default value is ascending from smallest to biggest. So how does this window work? Let's start with the first row and let's say we need to fill in this value. So I'm going to look at my power level. It is 30. And then the window says that I can only see rows where the power level is equal or smaller. And what are the rows where the power level is equal or smaller to 30? They're these rows over here. So effectively, this is the only part of the table that this window sees on the first row. And then take the sum over power. So sum over 30 is 30. Move on to the second row. The power level is 40. The window says I only see rows where the power level is smaller or equal. And this includes these two rows over here. Now take the sum of power over here, you get 70, put it in the cell. Third row, I have power level 50. I'm only seeing these rows. So take the sum of power over this, it's 120, put it in the cell. And I can continue like this until I get to the highest value in my dataset. It's 100. Never mind that it's not the last row, because both of the last two rows, they have the highest value. And when you look at this, when you come to this row and you look at 100 and you say, what's the window? What rows can I see? I can see all rows where power is 100 or less. And that basically includes all of the table, right? It includes all of the table. So when you take the sum of power, you will get the total sum. And in fact, you can see that in this case, the cumulative power is equal to the total power that we computed before, just as we would expect. So this is easy to see here because we have ordered our data conveniently, but it works in any case. And so what the order by does in a window function is that it makes sure that each row only sees rows which come before it given your ordering. So if I want to order from the smallest power to the biggest power, each row will only see rows that come before it in this ordering, so they have the same level of power or lower, but they don't have a higher level of power. So let us now take it to BigQuery and make sure it works as intended. And I will add an ordering by power. And here I will see the same thing that I've shown you in the spreadsheet. I notice now that some numbers are different, that these two items have 90 instead of 100, but never mind that, the logic is the same and the numbers make sense. Now I'm also able to change the direction of the ordering, right? So let's say that I take this field and copy it just the same, except that instead of ordering by power ascending, I order by power descending. So what do you expect to see in this case? Let's take a look. Now what I see here is that each item is going to look at its level of power, and then it's only going to consider items that are just as powerful or more powerful, right? So it's the exact same logic, but it's reversed. So when you look at the weakest item, potion, it has 30, and so it is looking at all the items because there's no weaker item. And so it finds the total level of power in our dataset. But if you go to the strongest item, like Excalibur, it has a power level of 100, and there's only two items in the whole dataset that have this power level, itself and the Phoenix Feather. So if you sum the power over these, you get 200. So you can see it's the exact same logic, but now each row only sees items that have the same level of power or higher. So when you order inside a window function, you can decide the direction of this ordering by using descending or ascending. Or if you are a lazy programmer, you can omit the ascending keyword and it will work just the same because that's the default. And finally, we want to compute the cumulative sum of power by type. And you might notice that it is in a way the combination of these two requirements. So let us see how to do that. Now, the first thing I want to do is to sort our data in order to help us. So I'm going to get this whole thing and I'm going to say sort range. I'm going to need the advanced options. I have a heading row. And so first of all, I want to order by type. And then within each type, I want to order by power. And this is our data now. Now, for each item, I want to show the cumulative sum of power, just like I did here, except that now I only want to do it within the same item type. So if we look at armor, it's already sorted, right? So I have power 40 and this is the smallest one, so I will just put 40 over here. Next I have this item with power 70, it's still armor, has power 70, and so I'm going to look at these two values and sum them up. Now I have 78, so I will take this plus 78, which is the sum of these three values. And finally, I have 90, which is the sum of those values. And now I'm done with armor, right? I'm beginning with a new item type. So I have to start all over again. I'm looking at potions now. So we start with 30, that is the smallest value. Then we move to 50. So this is now seeing 30 and 50, which is 80. Add 60 to 80, that is 140. And finally, we want to add 99 plus 140, which is another way of saying that we want to add these values, all the values for potion. So this is what we want, cumulative sum of power within item type. So we do it within the item type, and then when we find a new type, we start over. So to calculate it for weapon, I could copy my function from here, paste it in weapon, and then I would need to modify it, right? I would need the range to only include weapon. So that's from C10. So go here, C10 is the first one. And the value that I want to look at here would have to be C10 as well, because I want to start by looking at the power level for the first weapon. And for some reason it's purple. However, it should be correct. It should always be the sum of the previous value. So we start with 65, then we have 65 plus 75, 66, 75, 65, and so on. So this is our result. It's cumulative power within the item type. And to write this in SQL, I will take my previous query over here. And now when we define the window, we can simply combine what we've done before. We can combine the partition by with the order by. And you need to write them in the following order. First the partition and then the order. So I will partition by item type, and I will order by power, ascending. And this will achieve the required result. So for each row in this field, the window will be defined as follows. First, partition by item type, right? So first of all, you can only see rows which have the same item type as you have. But then within this partition, you have to keep only rows where the power is equal or smaller than what you have. So in the case of the first item, you only get this row. Likewise, in the case of the first potion item, you only get this row. If you look at the second armor item, again, it partitions, right? So it looks at all the items which have armor, but then it has to discard those that have a bigger power than itself. So it will be looking at these two rows. And if, for example, we look at the last row over here, so this row will say, oh, okay, I'm a weapon, so I can only see those that are weapon. And then I can only see those that have a level of power that's equal or smaller than mine. And that checks out. Those are all the rows. And in fact, the sum over here is equal to the sum of power by type, which is what we would expect. So once again, let us verify that this works in BigQuery. And I will actually want to order by item type and power, just so I have the same ordering as in my sheet. And I should be able to see that within armor, you have this like growing cumulative sum. And then once the item changes, it starts all over, right? It starts again at the first value, it grows, it accumulates, and then we're done with potions. And then we have weapons, and then again it starts, and then it grows, and it goes all the way to include the total sum of all powers in the weapon item type. So here's a summary of all the variants of windows that we've seen. We have seen 4 variants. Now, in all of those, for clarity, we've kept the aggregation identical, right? We're doing sum over the power field. But of course, you know that you can use any aggregate function here on any column which is compatible with that aggregate function. And then we have defined 4 different windows. The first one is the simplest one. There's actually nothing in the definition. We just say over. And this means that it will just look at all the table. So every row will see the whole table, and so every row will show you the total of power for the whole table. Simple as that. The second window is introducing a partition by item type. And what this means in practice is that each row will look at its own item type and then only consider rows which share the same exact item type. And so within those rows, it will calculate the sum of power. Third window, we have an ordering field. So what this means is that each row is going to look at its level of power because we are ordering by power. And then it's going to only see rows where the power level is equal or smaller. And the reason why we're looking in this direction is that when we order by power is implicitly understood that we want to order by power ascending. If instead we ordered by power descending, it would be the same, just in the opposite direction. Each row would look at its level of power and then only consider rows where power is equal or bigger. And then finally, we have a combination of these two, right? We have a window where we use both a partition and an order. And so what this means is that each row is going to look at its item type and discard all of the rows which don't have the same item type. But then within the rows that remain, it's going to apply that ordering. It's going to only consider rows which have the same level of power or lesser. So it's simply a combination of these two conditions. And this is the gist of how window functions work. First thing to remember, window functions provide aggregation, but they don't change the structure of the table. They just insert a specific value at each row, but after applying a window function, the number of rows in your table is the same. Second thing to remember is that in the window definition, you get to define what each row is able to see when computing the aggregation. So when you are thinking about window function, you should be asking yourself, what part of the table does each row see? What's the perspective that each row has? And there are two dimensions on which you can work in order to define these windows. One is the partition dimension and the other is the ordering dimension. The partition dimension cuts up the table based on the value of a column. So you will only keep rows that have the same value. The order dimension cuts up the table based on the ordering of a field. And then depending on ascending or descending, depending on the direction that you choose, you can look at rows that are after you in the ordering, or you can look at rows that are before you in the ordering. And you can pick either of these, right? Either partitioning or ordering, or you can combine them. And by using this, you can define all of the windows that you might need to get your data. Now, as a quick extension of this, I want to show you that you're not limited to defining windows on single fields, on single columns. You can list as many columns as you want. So in this example, I'm going to the fantasy characters table. I'm getting a few columns, and then I'm defining an aggregation on a window function. So I'm taking the level field and I'm summing it up, and then I'm partitioning by two fields actually, by guild and is alive. So what do you expect to happen if I do this? This is actually the exact same logic as grouping by multiple fields, which we've seen in the group by. Now the data is not going to be divided by guild and is not going to be divided by whether the character is alive or not, but by all the mutual combinations between these fields. Okay, so Mirkwood and true is one combination, and so the people in here are going to fit together, right? So in fact, we have two characters here, 22 and 26, and their sum is 48. So you can see here that they both get 48 for sum of level. And likewise, when you look at Shirefolk true, these three, they all end up in the same group. And so they all share the same sum of level, which is 35. But Shirefolk false, this is another group, and they're actually alone, right? It's 12, and then the sum is 12. So again, when you partition by multiple fields, the data is divided in groups that are obtained by all the combinations between the values that these fields can have. And if you experiment a bit by yourself, you should have an easier time to convince yourself of this. Likewise, the same idea applies to the order part of a window. We have until now, for simplicity, ordered by one field. To be honest, most times you will only need to order by one field, but sometimes you might want to order by different fields. So in this example, you can see that we are defining our ordering based on two fields, power and then weight. And then based on that ordering, we calculate the sum of power, and this is again a case of cumulative sum. However, now the ordering is different, and you will realize this if we go to the most powerful items in our data, these last two, which are both at 100. So if you remember, when we were ordering by power alone, these two fields had the same value in this window function, because when you order just by power, they are actually the same. They both have 100. But because now we're ordering by weight, and again, we're ordering by weight ascending, so from the smallest weight to the biggest weight, now the Phoenix Feather comes first, because although it has the same power as Excalibur, the Phoenix Feather is lighter. And because it comes first, it has a different value for this aggregation. And of course, we have the power to say ascending or descending on each of the fields by which we order. So if I wanted to reverse this, I could simply write descending after the weight, and be careful that in this case, descending is only referring to weight, it's not referring to power. So this is just as if I've wrote this, right? So this one can be omitted because it's ascending by default, but I would write both to be clear. And now if I run this, you will see that our result is reversed, right? Excalibur comes first because we have weight descending, so it's heavier. And then last we have the Phoenix Feather, which is lighter. And again, understanding this theoretically is one thing, but I do encourage you to experiment with this, with your data, with exercises, and then you will be able to internalize it. And now we are back to our schema for the logical order of SQL operations, and it is finally complete again because we've seen all of the components that we can use to assemble our SQL query. And now the question is, where do window functions fit into this? Well, as you can see, we have placed them right here. So what happens is that, again, you get your data, and then the where filter runs, dropping rows which you don't need. And then you have a choice whether to do a group by, right? Now, if you do a group by, you're going to change the structure of your table. It's not going to have the same number of rows. It's going to have a number of rows that depends of the unique values of your grouping field or the unique combinations of values of your fields if you have used more than one. If you group, you will probably want to compute some aggregations, and then you may want to filter on those aggregations, meaning dropping rows based on the values of those aggregations. And here is where window functions come into play. It is on this result that window functions work. So if you haven't done a group by, then window functions will work on your data after the where filter runs. If you have done a group by, window functions will work on the result of your aggregation. And then after applying the window function, you can select which columns you want to show, give them labels, and then all the other parts run, right? So you can choose to drop duplicates from your result, meaning duplicate rows which have the same value on every column. You can stack together different tables, right? You can put them on top of each other. And then finally, when you have your result, you can apply some ordering, and also you can cut the result. You can limit it so you only show a few rows. And this is where window functions fit into the big scheme of things. And there are some other implications of this ordering. One interesting one is that if you have computed aggregations, such as the sum of a value within a class, you can actually use those aggregations in the window function. So you can sort of do an aggregation of an aggregation. But this is, in my opinion, an advanced topic, and it doesn't fit into this fundamentals course. It may fit someday in a later, more advanced course. I want to show you another type of window functions which are very commonly used and very useful in SQL challenges and SQL interviews. And these are numbering functions. Numbering functions are functions that we use in order to number the rows in our data according to our needs. And there are several numbering functions, but the three most important ones are, without any doubt, row number, dense rank, and rank. So let's see how they work in practice. Now what I have here is a part of my inventory table. I'm basically showing you the item ID and the value of each number. And conveniently, I have ordered our rows by value ascending, okay? And now we're going to number our rows according to the value by using these window functions. Now, I've already written the SQL query that I want to reproduce. So I'm going to the fantasy inventory table, and then I'm selecting the item ID and the item value, as you see here. And then I'm using three window functions. So the syntax is the same as what we've seen in the previous exercise, except that now I'm not using an aggregation function over a field like I did before when I was doing sum of power and so on, but I'm using another type of function. This is a numbering function, okay? So these functions over here, they don't actually take a parameter. As you can see, that there's nothing between these round brackets because I don't need to provide it an argument or a parameter. All I need to do is to call the function. But what's really important here is to define the correct window. And as you can see in the three examples here, the windows are all the same. I am simply ordering my rows by value ascending, which means that when it's going to compute the window function, every row will look at its own value and then say, okay, I'm only going to see rows where the value is the same or smaller. I'm not going to be able to visualize rows where the value is bigger than mine. And this is what the window does. So the first row over here will only see value of 30. The second row will see these. The third row will see these, and so on up until the last row, which will see itself and all the other rows as well. Now let us start with row number. So row number is going to use this ordering over here in order to number my rows. And it's as simple as saying, putting 1 in the first row, 2 in the second one, 3, 4, and so on. So if I extend this pattern, I'm going to get a number for every row. And that's it. That's all that row number does. It assigns a unique integer number to every row based on the ordering that's defined by the window function. And you might think, oh, big deal. Why do I need this? Don't I already have like row numbers over here in the spreadsheet? Well, in SQL problems, you often need to order things based on different values. and row number allows you to do this. You can also have many different orderings coexisting in the same table based on different conditions, and that can come in handy, as you will discover if you do SQL problems. Now let's move on to ranking. So first of all, we have dense rank, okay? And ranking is another way of counting, but is slightly different. Sometimes you just want to count things, you know, sometimes like we did here in row number, like, I don't know, you are a dog sitter and you're given 20 dogs and you getting confused between all their names, and then you assign a unique number to every dog so that you can identify them. And you can sort them by, I don't know, by age or by how much you're getting paid to dog sit them. Sometimes, on the other hand, you want to rank things, like when choosing which product to buy or expressing the results of a race, right? And the difference between ranking and counting can be seen when you have the same value, right? So when you want to simply number, like we did here, when you want to simply assign a different number to each element, and two things have the same value, then you don't really care, right? You need to sort of arbitrarily decide that, okay, one of them will be number 2 and one of them will be number 3. But you cannot do the same for ranking. If two students in a classroom get the best score, you can't just randomly choose that one of them is number 1 and the other is number 2. They have to both be number 1, right? And if two people finish a race at the same time and it's the best time, you can't say that one won the race and the other didn't, that because one is number 1, the other is arbitrarily number 2. They both have to be number 1, right? They have to share that rank. And this is where ranking differs. So let's go in here and apply our rank. Now we are ordering by value ascending, which means that the smallest value will have rank number 1. And so 30 has rank number 1. Now we go to the second row. And again, remember, window functions, that you always have to think row by row. You have to think what each row sees and what each row decides. So again, the row is going to order by value. So it's only going to see these values over here, and it has to decide its rank. So this row says, oh, I'm not actually number 1 because there is a value which is smaller than me. So that means I have to be number 2. And then we get to the third row. And this row is seeing all the values that come before it, right? They're equal or smaller. And now it's saying, oh, I'm not number 1 because there's something smaller, but then the value 50, which this guy has, is rank 2, and I have the same value, number 50. We arrived in the same spot, so I must have the same rank. Okay, and this is the difference between row number and rank, that identical values get the same rank, but they don't get the same row number. And now we come to this row, which is 60. So it's going to look back and it's going to say, oh, from what I see, 30 is the smallest one, so it has a rank of 1. And then you have 50 and 50. They both share a rank of 2, but I am bigger, so I need a new rank. And so what am I going to pick now as a new rank? Well, I'm going to pick 3 because it's the next number in the sequence. Then the next one is going to pick 4. The next one is going to pick 5. And then we have 6. And then it proceeds in the following way. So I'll do it quickly now. So 7, 8, 9, 10, 11. And again, careful here, we're sharing the same value. So they are both 11. Next we can proceed to 12, 13. Again, the same value, right? So they have to share the 13th spot. 14, so 14 for 1700, and then 14 again, and then 15, and then 16. And this is what we expect to see when we compute the dense rank. And finally, we come to rank. Now, rank is very similar to dense rank, but there is one important difference. So let's do this again. Smallest value has rank number 1, like before. And then we have 50, which has rank number 2. And then 50 is once more sharing rank number 2. And now we move from 50 to 60, so we need a new rank. But instead of 3, we put 4 over here. Why do we put 4? Because the previous rank covered 2 rows, and it sort of ate the 3. It sort of expanded to ate the 3. So based on the rules of simply rank, we have to lose the 3 and put 4 over here. So this is just another way of managing ranking, and you will notice that it conveys another piece of information compared to dense rank, because not only I see that this row over here has a different rank than the previous row, but I can also see how many members were covered by the previous ranks. I can see that in the previous ranks, they must have involved 3 members because I'm at 4 already. And this piece of information was not available for dense rank. So I will continue over here, and so I have a new value, which is rank 5, and then I have rank 6, rank 7, rank 8, rank 9, rank 10, rank 11. Now I have rank 12, and again I have to share the rank 12 because 2 identical values. But now, because 12 has eaten up 2 spots, I can't use the 13 anymore. The second 12 has like eaten the 13, and so I need to jump straight to 14. 15, 15 again, and now I have to jump to 17 because 15 had 2 spots. 17 again, and now I have to jump to 19, and then finally I have 20. So you can see that the final number is 20 for rank, just as with row number, because it's not only differentiating between ranks, but it's also counting for me how many elements have come before me, how many rows are contained in the previous ranks. I can tell that there's 19 rows in the previous ranks because of how rank works. Whereas with dense rank, we ended up using only 16, ended up being only up to 16. So we sort of lost information on how many records we have. And this might be one of the reasons why by default you have this method of ranking instead of this method of ranking, even though dense rank seems more intuitive when you are building the ranking yourself. So we can now take this query, and hopefully I've written it correctly, and go to BigQuery and try to run it. And as you can see, we have our items. They are sorted by value. And then we have our numbering functions. So row number should go from 1 to 20 without any surprises because it's just numbering the rows. Dense rank should have rank 1 for the first, and then these two should share the same rank because they both have 50, and then the next rank is 3. So just as I've shown you in the spreadsheet. Similarly here you have 11, 11, and then 12. Rank instead starts off just the same. Smallest value has rank number 1, and the next 2 values have rank number 2. But then after using up 2 and 2, it's like you've used up the 3, so you jump straight to 4. And after doing 15 and 15, you jump straight to 17. After doing 17, 17, you jump straight to 19. And then the highest number here is 20, which tells you how many rows you're dealing with. Of course, what you see here are window functions. They work just the same as I've shown you. And so you could pick up rank and you could order by value descending, and then you will find the inverse of that rank in the sense that the highest value item will give you rank 1 and you will go from there. And the lowest value item will have sort of the biggest rank number. And rank is often used like this, you know, the thing that has the most of what we want, you know, the biggest salary, the biggest value, the most successful product. We rank it, we make it so that it's rank 1. It's like the first in our race. And then everyone else goes from there. And so we often have actually, we order by something descending when we calculate the rank. And of course, because these numbering functions are window functions, they can also be combined with partition by if you want to cut the data into subgroups. So here's an example on the fantasy characters table. We are basically partitioning by class, meaning that each row only sees the other rows that share the same class. So archers only care about archers, warriors only care about warriors, and so forth. And then within the class, we are ordering by level descending, okay? So the highest levels come first, and using these to rank the characters, okay? So if I go here, then I can see that within the archers, the highest level archer has level 26, so they get the first rank. And then all the others go down from there. And then we have our warriors. And the highest level warrior is 25, and they also get rank 1 because they are being ranked within warriors. So this is like when you have races and there are categories. This is like when you have a race and there are categories within the race. So there are like many people who arrive first because they arrive first in their category. It's not that everyone competes with everyone. And so on and so forth. You can see that each class of character has their own dedicated ranking. And you can check the BigQuery page on numbering function if you want to learn more about these functions. You can see here the ones we've talked about: rank, row number, and dense rank. There are a few more, but these are the ones that are most commonly used in SQL problems. And because I know that it can be a bit confusing to distinguish between row number, dense rank, and rank, here's a visualization that you might find useful. So let's say that we have a list of values, which are these ones, and we are ordering them in descending order. So you can see that there's quite some repetition in these values. And given this list of values, how would these different numbering functions work on them? Right, so here's row number. Row number is easy. It just assigns a unique number to each of them. So it doesn't matter that the values are sometimes the same. You sort of arbitrarily pick one to be 1, the other to be 2, and then you have 3, and then here you have 10, 10, 10, but it doesn't matter. You just want to order them, so you do 4, 5, 6, and then finally 7. Dense rank is actually cares about the values being the same. So 50 and 50, they both get 1. 40 gets 2. And then the 10s get 3, and then 5 gets 4. So easy, the rank just grows using all the integer numbers. Dense rank is also assigning rank 1 to 50 and 50, but it's also throwing away the 2 because there are 2 elements in here. Then the next one is getting rank 3 because the 2 has already been used. And then the next batch, 10, 10, 10, is getting rank 4, but it's also burning 5 and 6. And the next one then can only get rank 7. So these are the differences between row number, dense rank, and rank visualized. We have now reached the end of our journey through the SQL fundamentals. I hope you enjoyed it, and I hoped that you learned something new. You hopefully now have some understanding of the different components of SQL queries and the order in which they work and how they come together to allow us to do what we need with the data. Now, of course, learning the individual components and understanding how they work is only half the battle. The other half of the battle is, how do I put these pieces together? How do I use them to solve real problems? And in my opinion, the response to that is not more theory, but it's exercises. Go out there and do SQL challenges. do SQL interviews, find exercises, or even better, find some data that you're interested in, upload it in BigQuery, and then try to analyze it with SQL. I should let you know that I have another playlist where I am solving 42 SQL exercises in PostgreSQL. And I think this can be really useful to get the other half of the course, which is doing exercises and knowing how to face real problems with SQL. And I really like this playlist because I'm using a free website, a website that doesn't require any sign up or any login. It just works. And you get a chance to go there and do all of these exercises that cover all the theory that we've seen in this course. And then after trying it yourself, you get to see me solving it and my thought process and my explanation. And I think it can be really useful if you want to deepen your SQL skills. But in terms of how do I put it all together, how do I combine all of this stuff, I do want to leave you with another resource that I have created, which is this table. And this table shows you the fundamental moves that you will need to do whenever you do any type of data analytics. And I believe that every sort of analytics that you might work on, no matter how simple or complicated, can ultimately be reduced to these few basic moves. And what are these moves? They should actually be quite familiar to you by now. So we have joining, and this is where we combine data from multiple tables based on some connections between columns. And in SQL, you can do that with the join. Then we have filtering. Filtering is when we pick certain rows and discard others. So, let's look only at customers that joined after 2022. Now, how do you do that in SQL? There are a few tools that you can use to do that. The most important one is the where filter. And the where filter comes in action right after you've loaded your data, and it decides which rows to keep, which rows to discard. Having does just the same, except that it works on aggregated fields. It works on fields that you've obtained after a group by. Qualify, we actually haven't seen it in this course because it's not a universal component of SQL. Certain systems have it, others don't. But qualify is basically also a filter, and it works on the result of window functions. And finally, you have distinct, which runs quite at the end of your query, and it's basically removing all duplicate rows. And then of course you have grouping and aggregation. And we've seen this in detail in the course. You subdivide the data on certain dimensions, and then you calculate aggregate values within those dimensions. Fundamental for analytics. How do we aggregate in SQL? We have the group by, we have the window functions, and for both of them we use aggregate functions such as sum, average, and so on. And then we have column transformations. So this is where you apply logic, arithmetic, to transform columns, combine column values, and take the data that you have in order to compute data that you need. And we do this where we write the select, right? We can write calculations that involve our columns. We have the case when, which allows us to have a sort of branching logic and decide what to do based on some conditions. And of course, we have a lot of functions that make our life easier by doing specific. Next, we have union. Union is pretty simple. Take tables that have the same columns and stack them together, meaning put their rows together and combine them. And finally, we have sorting, which can change how your data is sorted when you get the result of your analysis, and can be also used in window functions in order to number or rank our data. And these are really the fundamental elements of every analysis and every SQL problem that you will need to solve. So one way to face a problem, even if you are finding it difficult, is to come back to these fundamental components and try to think of how do you need to combine them in order to solve your problem. And how can you take your problem and break it down to simpler operations that involve these steps. Now, at the beginning of the course, I promised you that we would be solving a hard SQL challenge together at the end of the course. So here it is. Let us try now to solve this challenge, applying the concepts in this course. Now, as a quick disclaimer, I'm picking a hard challenge because it's sort of fun and it gives us a playground to showcase several concepts that we've seen in the course, and also because I would like to show you that even big, hard, scary challenges that are marked as hard and even have advanced in their name can be tackled by applying the basic concepts of SQL. However, I do not intend for you to jump into these hard challenges from the very start. It would be much better to start with basic exercises and do them step by step, and be sure that you are confident with the basic steps before you move on to more advanced steps. So if you have trouble approaching this problem or even understanding my solution, don't worry about it. Just go back to your exercises and start from the simple ones and then gradually build your way up. That being said, let's look at the challenge, Marketing Campaign Success Advanced on Strata Scratch. So first of all, we have one table that we will work on for this challenge, Marketing Campaign. So Marketing Campaign has a few columns and it actually looks like this. Okay, so there's a user ID, created at, product ID, quantity, price. Now, when I'm looking at the new table, the one question that I must ask to understand it is, what does each row represent? And just by looking at this table, I can have some hypotheses, but I'm actually not sure what each row represents. So I better go and read the text until I can get a sense of that. So let's scroll up and read. You have a table of in-app purchases by user. Okay, so this explains my table. What does each row represent? It represents an event that is a purchase. Okay, so it means that user ID 10 bought product ID 101 in a quantity of 3 at the price of 55, and created that tells me when this happened. So this happened 1st of January 2019. So great, now I understand my table and now I can see what the problem wants from me. Let's go on and read the question. So I have a table of in-app purchases by users. Users that make their first in-app purchase are placed in a marketing campaign where they see call to actions for more in-app purchases. Find the number of users that made additional purchases due to the success of the marketing campaign. The marketing campaign doesn't start until 1 day after the initial app purchase. So users that made one or multiple purchases on the first day do not count, nor do we count users that over time purchase only the products they purchased on the first day. All right, so that was a mouthful, okay? So this on the first run, it's actually a pretty complicated problem. So our next task now is to understand this text and to simplify it to the point that we can convert it into code, okay? And a good intermediate step before jumping into the code is to write some notes, and we can use the SQL commenting feature for that. So what I understand from this text is that users make purchases and we're interested in users that make additional purchases. We're interested in users who make additional purchases thanks to this marketing campaign. How do we define additional purchases? Additional purchase is defined as, and the fundamental sentence is this one: users that made one or multiple purchases on the first day do not count. So additional purchase happens after the first day, right? nor do we count users that over time purchase only the products they purchased on the first day. So the other condition that we're interested in is that it involves a product that was not bought the first day. And finally, what we want is the number of users. So get the number of these users. That should be a good start for us to begin writing the code. So let us look at the marketing campaign table again, and I remind you that each row represents a purchase. So what do we need to find first in this table? So we want to compare purchases that happen on the first day with purchases that happen the following day. So we need a way to count days. And what do we mean first day and following days? Do we mean the first day that the shop was open? No, we actually mean the first day that the user ordered, right? Because the user signs up, does the first order, and then after that the marketing campaign starts. So we're interested in numbering days for each user such that we know what purchases happened on the first day, what purchases happened on the second day, third day, and so on. And what can we use to run a numbering by user? We can use a window function with a numbering function, right? So I can go to my marketing campaign table and I can select the user ID and the date in which they bought something and the product ID for now. Now I said that I need a window function. So let me start and define the window. Now I want to count the days within each user. So I will actually need to partition by user ID so that each row only looks at the rows that correspond to that same user. And then there is an ordering, right? There is a sequence from the first day in which the user bought something to the second and the third and so on. So my window will also need an ordering. And what column in my table can provide an ordering? It is created at. And then what counting function do I need to use here? Well, the way to choose is to say, what happens when the same user made two different purchases on the same date? What do I want my function to output? Do I want it to output two different numbers as a simple count, or do I want it to output the same number? And the answer is that I want it to output the same number because all of the purchases that happened on day one need to be marked as day one, and all the purchases that happened on day two need to be marked as day two, and so on. And so the numbering function that allows us to achieve this is rank. And if you remember, ranking works just like ranking the winners of a race. Everyone who shares the same spot gets the same number, right? And this is what we want to achieve here. So let us see what this looks like now, and let us order by user ID and created at. Let us now see our purchases. Now, user 10 started buying stuff on this day. They bought one product and the rank is 1. Let us actually give a better name to this column so that it's not just rank. And we can call it user day. All right. So this user ID 10 had first user day on this date and they bought one product. Then at a later date, they had their second user day and they bought another product, and then they had a third. Now, user 14 started buying on this date. This was their first user day. They bought product 109. And then the same day, they bought product 107. And this is also marked as user day 1. So this is what we want. And then at a later day, they bought another product. And this is marked as user day 3. Remember, with rank, you can go from 1, 1 to 3 because the spot marked as 1 has eaten the spot marked as 2. That's not an issue in this problem, so we are happy with this. Now, if we go back to our notes, we see that we are interested in users who made additional purchases, and additional means that it happens after the first day. And how can we identify purchases that happened after the first day? Well, there's a simple solution for this. We can simply filter out rows that have a user day 1. Right? All of the rows where the user day is 1 represent purchases that the user made on their first day. So we can discard these and keep only purchases that happened on the following days. Now, I don't really have a way to filter on this window function because, as you recall from the order of SQL operation, the window function happens here and the where filter happens before that. So the where filter cannot be aware of what happens in the window function, and the having also happens before it. So I need a different solution to filter on this field. What I need to do is to use a common table expression so that I can break this query in 2 steps. So I'm going to wrap this logic into a table called T1, or I can call it purchases for it to be more meaningful. And if I do select star from purchases, you will see that the result does not change. But what I can do now is to use the where filter and make sure that the user day is bigger than 1. And if I look here, you will see that I have all purchases which happened after the user's first day. But there is yet one last requirement that I have to deal with, which is that the purchase must happen after the first day and it must involve a product that the user didn't buy on the first day. So how can I comply with this requirement? Now, for all of the rows that represent a purchase, I need to drop the rows that involve a product ID that the user bought the first day. So if I find out that user 10 bought product 119 on day 1, this purchase does not count. I'm not interested in it. So how can I achieve this in code? I'm already getting all the purchases that didn't happen on day 1, and then I want another condition. So I will say and product ID not in, and here I will say products that this user bought on day 1. Right? It makes sense. So this is all the filters I need to complete my problem. Show me all the purchases that happened not on day 1, and also make sure that the user didn't buy this product on day 1. So what I need to do is to add a subquery in here. And before I do that, let me give an alias to this table so that I don't get confused when I call it again in the subquery. So this first version of purchases that we're using, we could call it next days because we're only looking at purchases that happen after the first day. Whereas in the subquery, we want to look at purchases, but we're interested in the ones that actually happened on day 1. So we could call this first day. And we can use a where filter to say that first day user day needs to be equal to 1. So this is a way that we can use to look at the purchases that happened on the first day. Now, when we make this list, we need to make sure that we are looking at the same user, right? And to do that, we can say, and first day user ID needs to be the same as next day's user ID. And this ensures that we're looking at the same user and we're not getting confused between users. And finally, what do we need from the list of first day purchases? We need the list of products. So let me first see if the query runs. So it runs, there's no mistakes. And now let us review the logic of this query. We have purchases, which is basically a list of purchases with the added value that we know if it happened on day 1, on day 2, on day 3, and so on. And then we are getting all of these purchases, the ones that happened after day 1. And we are also getting the list of products that this user bought on day 1. And we are making sure to exclude those products from our final list. And this is a correlated subquery because it is a specific SQL query that provides different results for every row, that must run for every row. Because in the first row, we need to get the list of products that user ID 10 has bought on day 1 and make sure that this product is not in it. And then when we go to another row, such as this one, we need to get the list of all products that user 13 bought on day 1 and make sure that 118 is not in those products. So this is why it's a correlated subquery. And the final step in our problem is to get the number of these users. So instead of selecting star and getting all of the columns, I can say count distinct user ID. And if I run this, I get 23. Checking, and this is indeed the right solution. So this is one way to solve the problem, and hopefully it's not too confusing, but if it is, don't worry, it is after all an advanced problem. If you go to solution here, I do think, however, that my solution is a bit clearer than what StrataScratch provides. This is actually a bit of a weird solution, but that's ultimately up to you to decide. And I am grateful to StrataScratch for providing problems that I can solve for free, such as this one. Welcome to PostgreSQL Exercises, the website that we will use to exercise our SQL skills. Now, I am not the author of this website. I'm not the author of these exercises. The author is Alasdair Owens, and he has generously created this website for anyone to use, and it's free. You don't even need to sign up. You can go here right away and start working on it. I believe it is a truly awesome website. In fact, the best at what it does. And I'm truly grateful to Alasdair for making this available to all. The way the website works is pretty simple. You have a few categories of exercises here, and you can select a session. And once you select a session, you have a list of exercises. You can click on an exercise, and then here in the exercise view, you have a question that you need to solve, and you see a representation of your 3 tables. We're going to go into this shortly, and then you see your expected results. And here in this text box over here, you can write your answer and then hit run to see if it's the correct one. The results will appear in this lower quadrant over here. And if you get stuck, you can ask for a hint. Here there are also a few keyboard shortcuts that you can use. And then after you submit your answer, or if you are completely stuck, you can go here and see the answers and discussion. And that's basically all there is to it. Now let's have a brief look at the data and see what that's about. And the data is the same for all exercises. And what we have here is the data about a newly opened country club. And we have 3 tables here. Members represents the members of the country club. So we have their surname and first name, their address, their telephone, and the date at which they joined, and so on. And then we have the bookings. So whenever a member makes a booking into a facility, that event is stored into this table. And then finally, we have a table of facilities where we have information about each facility. And in there we have some tennis courts, some badminton courts, massage rooms, and so on. Now, as you may know, this is a standard way of representing how data is stored in a SQL system. So you have the tables, and for each table you see the columns, and for each column you see the name and then the data type, right? So the data type is the type of data that is allowed into this column. And as you know, each column has a single data type, and you are not allowed to mix multiple data types within each column. So we have a few different data types here, and they have the Postgres name. So in Postgres, an integer is a whole number, like 1, 2, 3, and a numeric is actually a floating point number, such as 2.5 or 3.2. Character varying is the same as string. It represents a piece of text. And if you wonder about this number in round brackets, 200, it represents the maximum limit of characters that you can put into this piece of text. So you cannot have a surname that's bigger than 200 characters. And then you have a timestamp, which represents a specific point in time. And this is actually all the data types that we have here. And finally, you can see that the tables are connected. So in the bookings table, every entry, every row of this table represents an event where a certain facility ID was booked by a certain member ID at a certain time for a certain number of slots. And the facility ID is the same as the facility ID field in facilities, and the MEMID field is the same as the MEMID or member ID field in members. Therefore, the bookings table is connecting to both of these tables, and these logical connections will allow us to use joins in order to build queries that work on all of these 3 tables together, and we shall see in detail how that works. Finally, we have an interesting arrow over here which represents a self relation, meaning that the members table has a relation to itself. And if you look here, this is actually very similar to the example that I have shown in my mental models course. For each member, we can have a recommended by field, which is the ID of another member, the member who recommended them into the club. And this basically means that you can join the members table to itself in order to get at the same time information about a specific member and about the member who recommended them, and we shall see that in the exercises. And clearly the exercises run on PostgreSQL, and Postgres is one of the most popular open source SQL systems out there. PostgreSQL is a specific dialect of SQL which has some minor differences from other dialects such as MySQL or Google SQL that is used by BigQuery, but it is mostly the same as all the others. If you've learned SQL with another dialect, you're gonna be just fine. PostgreSQL does have a couple of quirks that you should be aware about, but I will address them specifically as we solve these exercises. Now, if you want to rock these exercises, I recommend keeping in mind the logical order of SQL operations. And this is a chart that I have introduced and explained extensively in my mental models course, where we actually start with this chart being mostly empty and then we add one element at a time, making sure that we understand it in detail. So I won't go in depth on this chart now, but in short, this chart represents the logical order of SQL operations. These are all the components that we can assemble to build our SQL queries. They're like our Lego building blocks for SQL. And these components, when they're assembled, they run in a specific order, right? So the chart represents this order. It goes from top to bottom. So first you have from, then you have where, and then you have all the others. And there are two very important rules: that each operation can only use data produced above it, and an operation doesn't know anything about data produced below it. So if you can keep this in mind and keep this chart as a reference, it will greatly help you with the exercises. And as I solve the exercises, you will see that I put a lot of emphasis on coming back to this order and actually thinking in this order in order to write effective queries. Let us now jump in and get started with our basic exercises. So I will jump into the first exercise, which is retrieve everything from a table. So here I have my question, and how can I get all the information I need from the facilities table? And as you know, all my data is represented here, so I can check here to see where I can find the data that I need. Now, as I write my query, I aim to always start with the from part. Why start with the from part? First of all, it is the first component that runs in the logical order. So again, if I go back to my chart over here, I can see that the from component is the first. And that makes sense, right? Because before I do any work, I need to get my data. So I need to tell SQL where my data is. So in this case, the data is in the facilities table. Next, I need to retrieve all the information from this table. So that means I'm not going to drop any rows, and I'm going to select all the columns. And so I can simply write select star. And if I hit run, I get the result that I need. Here in this quadrant, I can see my result and it fits the expected results. Now the star is a shortcut for saying, give me all of the columns of this table. So I could have listed each column in turn, but instead I took a shortcut and used a star. Retrieve specific columns from a table. I want to print a list of all the facilities and their cost to members. So as always, let's start with the from part. Where is the data that we need? It's in the facilities table again. And now the question is actually not super clear, but luckily I can check the expected results. So what I need are two columns from this table, which is name and member cost. So to get those two columns, I can write select name member cost. Hit run and I get the result that I need. So if I write select star, I'm gonna get all the columns of the table, but if I write the name of specific columns separated by comma, I will get only those columns specifically. Control which rows are retrieved. We need a list of facilities that charge a fee to members. So we know that we're going to work with the facilities table, and now we need to keep certain rows and drop others. We need to keep only the rows that charge a fee to members. So what component can we use in order to do this? If I go back to my components chart, I can see that right after from, we have the where component. And the where component is used to drop rows that we don't need, right? So after getting the facilities table, I can say where member cost is bigger than 0, meaning that they charge a fee to members. And finally, I can get all of the columns from this. Control which rows are retrieved, part 2. So like before, we want a list of facilities that charge a fee to members, but our filtering condition is now a bit more complex because we need that fee to be less than 1/50th of the monthly maintenance cost. So I copied over the code from the last exercise. We're getting the data from our facilities list and we're filtering for those where the member cost is bigger than 0. And now we need to add a new condition, which is that fee, which is member cost, is less than 1/50th of the monthly maintenance cost. So I can take monthly maintenance over here and divide it by 50, and I have my condition. Now, when I have multiple logical conditions in the where, I need to link them with the logical operator so SQL can figure out how to combine them, because the final result of all my conditions needs to be a single value, which is either true or false, right? So let's see how to do this. In my mental models course, I introduced the Boolean operators and how they work, so you can go there for more detail. But can you figure out which logical operator do we need here to chain these two conditions? As suggested in the question, the operator that I need is AND, so I can put it here. And what AND does is that both of these conditions need to be true for the whole expression to evaluate to true and for the row to be kept. So only the rows where both of these conditions are true will be kept, and all other rows will be discarded. Now, to complete my exercise, I just need to select a few specific columns because we don't want to return all the columns here. And I think that I will cheat a bit by copying them from the expected results and putting them here. But normally you would look at the table schema and figure out which columns you need. And that completes our exercise. Basic string searches produce a list of all facilities with the word tennis in their name. So where is the data we need? It's in the CD facilities table. Next question, do I need all the rows from this table or do I need to filter out some rows? Well, I only want facilities with the word tennis in their name, so clearly I need a filter. Therefore, I need to use the where statement. How can I write the where statement? I need to check the name, and I need to keep only facilities which have tennis in their name. So I can use the like statement here to say that the facility needs to have tennis in its name, but what these wildcards signify is that we don't care what precedes tennis and what follows tennis. It could be 0 or more characters before it and after it. We just care to check that they have tennis in their name. And finally, we need to select all the columns from these facilities. And that's our result. Beware, like I said before, of your use of the quotes. So what you have here is a string. It's a piece of text that allows you to do your match. Therefore, you need single quotes. If you, as it's likely to happen, used double quotes, you would get an error here, and the error tells you that the column tennis does not exist because double quotes are used to represent column names and not pieces of text. So be careful with that. Matching against multiple possible values. Can we get the details of facilities with ID 1 and ID 5? So where is my data? Is in the facilities table. And do I need all the rows from this table or only certain ones? I need only certain rows. because I want those that have ID 1 and ID 5. So I need to use a where statement. Now, what are my conditions here? Their ID, actually facility ID equals 1 and facility ID equals 5. So I have my two logical conditions. Now, what operator do I need to use in order to chain them? I need to use the OR operator, right? Because only one of these needs to be true in order for the whole expression to evaluate to true. And in fact, only one of them can be true because it's impossible for the ID of a facility to be equal to 1 and 5 at the same time. Therefore, the AND operator would not work, and what we need is the OR operator. And finally, we need to get all the data, meaning all the columns about this facility, so I will use select star. The problem is now solved, but now let's imagine that tomorrow we need this query again and we need to include another ID, ID 10. So what we can do is put OR facility ID equals 10. But this is becoming a bit unwieldy, right? Because imagine having a list of 10 IDs and then writing OR every time, and it's not very scalable as an approach. So as an alternative, we can say facility ID in and then list the values like 1 and 5. So if I take this and make it into my condition, I will again get the same result. I will get the solution, but this is a more elegant approach and it's also more scalable because it's much easier to come back and insert other IDs inside this list. So this is a preferred solution in this case. And logically, what in is doing is looking at the facility ID for each row and then checking whether that ID is included in this list. If it is, it returns true, therefore it keeps the row. If it's not, returns false, therefore it drops the row. And we shall see a bit later that the in notation is also powerful because in this case we have a static list of IDs. We know that we want IDs 1 and 5, but in more advanced use cases, instead of a static list, we could provide another query, a SQL query or a subquery that would dynamically retrieve a certain list, and then we could use that in our query. So we shall see that in later exercises. Classify results into buckets. Produce a list of facilities and label them cheap or expensive based on their monthly maintenance. So we want to get our facilities. Do we need a filter? Do we need to drop certain rows? No, we actually don't. We want to get all facilities and then we want to label them. And we need to select the name of the facility, and then here we need to provide the label. So what SQL statement can we use to provide a text label according to the value of a certain column? What we need here is a case statement which implements conditional logic, which implements a branching, right? It's similar to the if-else statements in other programming languages, because if the monthly maintenance cost is more than 100, then it's expensive. Otherwise, it's cheap. So this calls for a case statement. Now, I always start with case and end with end, and I always write these at the beginning so I don't forget them. And then for each condition, I write when and what is the condition that I'm interested in. Monthly maintenance being above 100. That's my first condition. What do I do in that case? I output a piece of text which says expensive. And remember, single quotes for text. Next, I could write the next condition explicitly, but actually, if it's not 100, then it's less than 100. So all I need here is an else. And in that case, I need to output a piece of text which says cheap. And finally, I have a new column and I can give it a label. I can call it cost. And I get my result. So whenever you need to put values into buckets or you need to label values according to certain rules, that's usually when you need a case statement. Working with dates. Let's get a list of members who joined after the start of September 2012. So looking at these tables, where is our data? It's in the members table. So I will start writing this. And now, do I need to filter this table? Yes, I only want to keep members that joined after a certain time. And now, how can I run the condition on this table? I can say where join date is bigger than 2012 September 01. So luckily in SQL and in Postgres, filtering on dates is quite intuitive. Even though here we have a timestamp that represents a specific moment in time up to the second, we can say bigger or equal actually, because we also want to include those who joined on the first day. We can write bigger or equal and just specify the date, and SQL will fill in the rest of the remaining values and the filter will work. And next we want to get a few columns for these members. So I will copy paste here, select, and this solves our query. Removing duplicates and ordering results. We want an ordered list of the first 10 surnames in the members table, and the list must not contain duplicates. So let's start by getting our table, which is the members table. Now we want to see the surnames. So if I write this, I will see that there are surnames which are shared by members, so there are actually duplicates here. So what can we do in SQL in order to remove duplicates? We have seen in the mental models course that we have the distinct keyword, and the distinct is going to remove all duplicate rows based on the columns that we have selected. So if I run this again, I will not see any duplicates anymore. Now the list needs to be ordered alphabetically, as I see here in the expected results, and we can do that with the order by statement. And when you use order by on a piece of text, the default behavior is that the text is ordered alphabetically. And if I were to use descending, then it would be ordered in reverse alphabetical order. However, that's not what I need. I need it in alphabetical order. So now I see that they are ordered. And finally, I want the first 10 surnames. So how can I return the first 10 rows of my result? I can do that with the limit statement. So if I say limit 10, I will get the first 10 surnames. And since I have ordered alphabetically, I will get the first 10 surnames in alphabetical order. And this is my result. Now, going back to our map over here, we have the from, which gets a table. We have a where, which drops rows that we don't need from that table. And then all the way down here, we have the select, which gets the columns that we need. And then we have the distinct, right? And the distinct needs to know which columns we need because it drops duplicates based on these columns. So in this example over here, we're only taking a single column, surname, so the distinct is going to drop duplicate surnames. And then at the end of it all, when all the processing is done, we can order our results. And then finally, once our results are ordered, we can do a limit to limit the number of rows that we return. So I hope this makes sense. Combining results from multiple queries. So let's get a combined list of all surnames and all facility names. So where are the surnames? They're in CD members. And from CD members, I can select surname, right? And this will give me the list of all surnames. And where are the facility names? There are in CD facilities, and I could say select name from CD facilities, and I would get a list of all the facilities. Now we have two distinct queries, and they both produce a list or a column of text values, and we want to combine them. What does it mean? We want to stack them on top of each other, right? And how does that work? Well, if I just say run query like this, I will get an error because I have two distinct queries here, and they're not connected in any way. But when I have two queries or more defining tables and I want to stack them on top of each other, I can use the union statement, right? And if I do union here, I will get what I want because all the surnames will be stacked vertically with all the names, and I will get a unique list containing both of these columns. Now, as I mentioned in the mental models course, typically when you have just union, it means union distinct, and actually other systems like BigQuery don't allow you to write just union. They want you to specify union distinct. And what this actually does is that after stacking together these two tables, it removes all duplicate rows. And the alternative to this is union all, which does not do this. It actually keeps all the rows. And as you know, we have some duplicate surnames and then we get them here and it doesn't fit with our result. But if you write just union, it will be union distinct and you won't have any duplicates. And if you look at our map for the logical order of SQL operations, we are getting the data from a certain table and filtering it and then doing all sorts of operations and on this data. And then we are selecting the columns that we need, and then we can remove the duplicates from this one table. And then what comes next is that we could combine this table with other tables, right? We can tell SQL that we want to stack this table on top of another table. So this is where the union comes into play. And only after we have combined all the tables, only after we have stacked them all up on top of each other, we can order the results and limit the results. Also remember, and I showed this in detail in the mental models course, when I combine two or more tables with a union, what I need is for them to have the exact same number of columns, and all of the columns need to have the same data type. So in this case, both tables have one column, and this column is a text, so the union works. But if I were to add another column here, and it's an integer column, it would not work because the union query must have the same number of columns, right? I will get an error. However, if I were to add an integer column in the second position in both tables, then it would work again, because again, I have the same number of columns and they have the same data type. Simple aggregation, I need the sign up date of my last member. So I need to work with the members table, and we have a field here which is join date, and I need to get the latest value of this date, the time when a member last joined, right? So how can I do that? I can take my join date field and run an aggregation on top of it. What is the correct aggregation in this case? It is max, because when it comes to dates, max will take the latest date, whereas min will take the earliest date. And I can label this as latest and get the result I need. Now, how aggregations work? They are functions that look like this. You write the name of the function, and then in round brackets you provide the arguments. The first argument is always the column on which to run the aggregation, and what the aggregation does is that it takes a list of values, could be 10, 100, a million, 10 million, it doesn't matter. It takes a long list of values and it compresses this list to a single value. It does like we've seen in this case, taking all of the dates and then returning the latest date. Now to place this in our map, we get the data from the table, we filter it, and then sometimes we do a grouping, which we shall see later in the exercises. But whether we do grouping or not, here we have aggregations. And if we haven't done any grouping, the aggregation works at the level of all the rows. So in the absence of grouping, as in this case, the aggregation will look at all the rows in my table, except for the rows that I've filtered away. But otherwise it will look at all the rows and then it will compress them into a single value. More aggregation. We need the first and last name of the last member who signed up, not just the date. So in the previous exercise, we saw that we can say select max join date from members, and we would get the last join date, the date when the last member signed up, right? So given that I want the first and the last name, you might think that you can say first name and surname in here, but this actually doesn't work. This gives an error. The error is that the column first name must appear in the group by clause or be used in an aggregate function. Now, the meaning behind this error and how to avoid it is described in detail in the mental models course in the group by section. But the short version of it is that what you're doing here is that with this aggregation, you're compressing join date to a single value, but you're doing no such compression or aggregation for first name and surname. And so SQL is left with the instruction to return something like this. And as you can see, here we have a single value, but for these columns, we have multiple values. And this does not work in SQL because you need all columns to have the same number of values. And so it throws an error. And what we really need to do here is to take this maximum join date and use it in a where filter, because we only want to keep that row which corresponds to the latest join date. So we can take the members table and get the row where join date is equal to the max join date. And from that, select the name and the surname. Unfortunately, this also doesn't work. So what we saw in the course is that you're not allowed to use aggregations inside where. So you cannot use max inside where. And the reason why is actually pretty clear, because aggregations happen at this stage in the process, and aggregations need to know whether a group by has occurred or not. They need to know whether they have to happen over all the rows in the table or only within the groups defined by the group by. And when we are at the where stage, the group by hasn't happened yet, so we don't know at which level to execute the aggregations. And because of this, we are not allowed to do aggregations inside the where statement. So how can we solve the problem now? Well, a sort of cheating solution would be if we knew the exact value of join date, we could place it here and then our filter would work. We're not using an aggregation, and we could put join date in here to display it as well, and that would work. However, this is a bit cheating, right? Because the maximum join date is actually a dynamic value. It will change with time. So we don't want to hard code it. We want to actually compute it. But because this is not allowed, what we actually need is a subquery. And the subquery is a SQL query that runs within a query to return a certain result. And we can have a subquery by opening round brackets here and writing a query. And in this query, we need to go to the members table and select the maximum join date. And this is our actual solution. So in this execution, you can imagine that SQL will go here inside the subquery, run this, get the maximum join date, place it in the filter, keep only the row for the latest member who has joined and then retrieve what we need about this member. Let us now move to the joins and subqueries exercises. The first exercise, retrieve the start times of members' bookings. Now, we can see that the information we need is spread out into tables because we want the start time for bookings, and that information is in the bookings table, but we want to filter to only get members named David Farrell, and the name of the member is contained in the members table. So because of that, we will need a join. So if we briefly look at the map for the order of SQL operations, we can see here that from and join are really the same step. And how this works is that in the from statement, sometimes all my data is in one table and then I just provide the name of that table. But sometimes I need to combine two or more different tables in order to get my data. And in that case, I would use the join. But everything in SQL works with tables, right? So when I take two or more tables and combine them together, at the end, all I get is just another table. And this is why from and join are actually the same component and they are the same step. So as usual, let us start with the from part, and we need to take the bookings table and we need to join it on the members table. And I can give an alias to each table to make my life easier. So I will call this book and I will call this mem. And then I need to specify the logical condition for joining this table. And the logical condition is that the memID column in the bookings table is really the same thing as the memID column in the members table. Concretely, you can imagine SQL going row by row in the bookings table and looking at the memID and then checking whether this memID is present in the members table. And if it's present, it combines the row, the current row from bookings with the matching row for members, does this with all the matching rows, and then drops rows which don't have a match. And we saw that in detail in the mental models course, so I'm not going to go in depth into it. Now that we have our table, which is comes from the join of members and bookings, we can properly filter it. And what we want is that the first name column is David in the column which comes from the members table, right? So mem.firstname is indicating the parent table and then the column name. And the surname is equal to Farrell. And remember, single quotes when using pieces of text. This is a where filter. You have two logical conditions, and then we use the operator AND because both of them need to be true. So now we have filtered our data, and finally we need to select the start times. And that's our query. Now remember that when we use join in a query, what's implied is that we are using inner join, and there are several types of join, but inner join is the most common, so it's the default one. And what inner join means is that it's going to return from the two tables that we're joining, is going to return only the rows that have a match, and all the rows that don't have a match are going to be dropped. So if there's a row in bookings and it has a memID that doesn't exist in the members table, that row will be dropped. And conversely, if there's a row in the members table and it has a memID that is not referenced in the bookings table, that row will also be dropped. And that's an inner join. Work out the start times of bookings for tennis courts. So we need to get the facilities that are actually tennis courts, and then for each of the facility we'll have several bookings, and we need to get the start time for those bookings, and it will be in a specific date. So we know that we need the data from these two tables because the name of the facility is here, but the data about the bookings is here. So I will go from CD facilities join CD bookings on. What are the fields that we can join on logically? Now let me first give an alias to these tables. So I will call this fax, and this I will call book. And now what I need to see is that the facility ID matches on both sides. Now we can work on our filters. So first of all, I only want to look at tennis courts. And if you look at the result here, it means that in the name of the facility, we want to see tennis. And so we can filter on string patterns, on text patterns by using the like command. So I can take facilities name and get it like tennis, and the percentage signs are wildcards, which means that tennis could be preceded and followed by 0 or more characters. We don't care, we just want to get those strings that have tennis in them. But that's not enough as a condition. We also need the booking to have happened on a specific date. So I will put an AND here. So AND is the operator we need because we're providing two logical conditions and they both need to be true. So AND is what we need. And then I can take the start time from the bookings table and say that it should be equal to the date provided in the instructions, because I want the booking to have happened in this particular date. However, this will not work. So I can actually complete the query and show you that it will not work, because here we get 0 results. So can you figure out why this command here did not work? Now I'm going to write a few comments here, and this is how you write them, and they are just pieces of text. They're not actually executed as code, and I'll just use them to show you what's going on. So the value for start time looks like this. So this is a timestamp and it's showing a specific point in time. But the date that we are providing for the comparison looks like this. So as you can see, we have something that is less granular because we're not showing all of this data about hour, minute, and second. Now, in order to compare these two things which are different, SQL automatically fills in this date over here. And what it does is that since there's nothing there, it puts zeros in there. And now that it has made this extension, it's going to actually compare them. So when you look at this comparison over here between these two elements, this comparison is false because the hour is different. Now when we write this filter command over here, SQL is looking at every single start time and then comparing it with this value over here, which is the very first moment of that date. But there's no start time that is exactly like this one. So basically this is always false, and thus we get 0 rows in our result. So what is the solution to this? When we take a start time from the data, before comparing it, we can put it into the date function. And if I take my example here, if I put it into the date function, it's going to drop that extra information about hour, minute, and second, and it's only going to keep the information about the date. So once I do this, if I pass it to the date function before comparing it to my reference date, now this one is going to become the result, which is this one, and then I'm going to compare it with my reference date, and then this is going to be true. So all this to say that before we compare start time with our reference date, we need to reduce its granularity and we need to reduce it to its date. So if I run the query now, I will actually get my start times. And after this, I just need to add the name. And finally, I need to order by time. So I need to order by book start time. There is still a small error here, so sometimes you just have to look at what you get and what's expected. And if you notice here, we are returning data about the table tennis facility, but we're actually just interested in tennis court. So what are we missing here? The string filter is not precise enough, and we need to change this into tennis court. And now we get our results. Produce a list of all members who have recommended another member. Now, if we look at the members table, we have all this data about each member, and then we know if they were recommended by another member. And recommended by is the ID of the member who has recommended them. And because of this, the members table, like we said, has a relation to itself because one of its column references its ID column. So let's see how to put this in practice. So to be clear, I simply want a list of members who appear to have recommended another member. So if I wanted just the IDs of these people, my task would be much simpler, right? I would go to the members table and then I could select recommended by, and then I will put a distinct in here to avoid repetitions. And what I would get here is the IDs of all members who have recommended another member. However, the problem does not want this because the problem wants the first name and surname of these people. So in order to get the first name and the surname of these people, I need to plug this ID back into the members table and get the data there. So for example, if I went to the members table and I selected everything where the mem ID is 11, then I would get the data for this first member. But now I need to do this for all members. So what I will have to do is to take the members table and join it to itself. And the first time I take the table, I'm looking at the members, quite simply. But the second time I take the members table, I'm looking at data about the recommenders of the members. So I will call this second instance Rex. So both of these, they come from the same table, but they're now two separate instances. And what is the logic to join these two tables? The members table has this recommended by field, and we take the ID from recommended by and we plug it back into the table, into memID, to get the data about the recommenders. And now we can go into the recommenders, which we got by plugging that ID, and get their first name and surname. I want to avoid repetition because a member may have been recommending multiple members, but I want to avoid repetition. So I will put a distinct to make sure that I don't get any repeated rows at the end. And then finally, I can order by surname and first name. And I get my result. So I encourage you to play with this and experiment a bit until it is clear. And in my mental models course, I go into depth into the self-join and do a visualization in Google Sheets that also makes it much clearer. Produce a list of all members along with the recommender. Now, if we look at the members table, we have a few columns and then we have the recommended by column. And sometimes we have the ID of another member who recommended this member. It can be repeated because the same member may have recommended multiple people. And then sometimes this is empty. And when this is empty, we have a null in here, which is the value that SQL uses to represent absence of data. Now, let us count the rows in members. So you might know that to count the rows of a table, we can do a simple aggregation, which is count star, and we get 31. And let's just make a note of this, that members has 31 rows, because in the result, we want a list of all members. So we must ensure that we return 31 rows in our results. Now I'm gonna delete this select. And as before, I want to go for each member and check the ID they have here in recommended by, and then plug this back into the table into memID so I can get the data about the recommender as well. And I can do that with a self join. So let me take members and join on itself. And the first time I will call it mems, and the second time I will call it rex. And the logic for joining is that in mems, recommended by is the same, is connected to rex memID. So this is taking the ID in the recommended by field and plugging it back into memID to get the data about the recommender. Now, what do I want from this? I want to get the first name of the member and the last name, surname, and then the first name and last name of the recommender. Surname. Great. So it's starting to look like the right result, but how many rows do we think we have here? And in order to count the rows, I can do select count star from, and then if I simply take this table, if I simply take this query and enclose it in brackets, now this becomes a subquery. So I can, the subquery must have an alias, so I can give it an alias like this, and I get 22. So how this works is that first SQL will compute the content of the subquery, which is the table that we saw before, and then it will, we need to assign it an alias, otherwise it doesn't work. This changes a bit by system, but in Postgres you need to do this. So we call it simply T1, and then we run a count star on this table to get the number of rows. And we see that the result has 22 rows. And this is an issue because we saw before that members has 31 rows and that we want to return all of the members. Therefore, our result should also have 31 rows. So can you figure out why are we missing some rows here? Now the issue here is that we are using an inner join. So remember, when we don't specify the type of join, it's an inner join. And what does an inner join do? It keeps only rows that have matches. So we saw before that in members, sometimes this field is empty. It has a null value because, maybe the member wasn't recommended by anyone. Maybe they just applied themselves. And what happens when we use this in an inner join and it has a null value? The row for that member will be dropped because obviously it cannot have a match with memID because null cannot match with anything, with any ID. And so that row is dropped and we lose it. However, that's not what we want to do. Therefore, instead of an inner join, we need to use a left join here. The left join will look at the left table, so the table that is left of the join command, and it will make sure to keep all the rows in that table, even the rows that don't have a match. In the rows that don't have a match, it will not drop them, it will just put a null in the values that correspond to the right table. And if I run the count again, I will get 31. So now I'm keeping all the members and I have the number of rows that I need. So now I can get rid of all of these because I know I have the right amount of rows, and I can get my selection over here. And it would actually help if we could make this a bit more ordered and assign aliases to the columns. So I will follow the expected results here and call this mem first name, mem surname, rec first name, rec surname. Now we have the proper labels, and you can see here that we always have the name of the member, but some member weren't recommended by anyone, and therefore for the first and last name of the recommender we simply have null values, and this is what the left join does. The last step here is to order, and we want to order by the last name and the first name of each member. And we finally get our result. So typically you use inner joins, which is the default join, because you're only interested in the rows from both tables that actually have a match. But sometimes you want to keep all the data about one table, and then you would put that table on the left side and do a left join, as we did in this case. Produce a list of all members who have used a tennis court. Now, for this problem, we need to combine data from all our tables, because we need to look at the members, and we need to look at their bookings, and we need to check what's the name of the facility for their bookings. So as always, let us start with the from part, and let us start by joining together all of these tables. cd facilities on facility ID, and then I want to also join on members, and that is my join. So we can always join 2 or more tables. In this case, we're joining 3 tables, and how this works is that the first join creates a new table, and then this new table is joined with the next one over here, and this is how multiple joins are managed. Now I have my table, which is the join of all of these tables, and we're only interested in members who have used the tennis court. If a member has made no bookings, we're not interested in that member, and so it's okay to have a join and not a left join. And for each booking we want to see the name of the facility, and if there was a booking who didn't have the name of the facility, we wouldn't be interested in that booking anyway, and so this join here also can be an inner join and doesn't need to be a left join. This is how you can think about whether to have a join or a left join. Now we want the booking to include a tennis court, so we can filter on this table, and we will look at the name of the facility and make sure that it has tennis court in it with the like operator. And now that we have filtered, we can get the first name and the surname of the member, and we can get the facility name. So here we have a starting result. Now in the expected result, we have merged the first name and the surname into a single string, and in SQL you can do this with the concatenation operator, which is basically taking two strings and putting them together into one string. Now, if I do this here, I will get something like this. And so this looks a bit weird. And what I want to do here is to add an empty space in between and again concatenate it. And now the names will look fine. I also want to label this as member and this other column as facility to match the expected results. Next, I need to ensure that there is no duplicate data. So at the end of it all, I will want to have distinct in order to remove duplicate rows. And then I want to order the final result by member name and facility name. So order by member and then facility. And this will work because the order by coming second to last, coming at the end of our logical order of SQL operations. Over here, the order by is aware of the alias, is aware of the label that I have put on the columns. And here I get the results that I needed. Not a lot happening here, to be honest. It's just that we're joining 3 tables instead of 2, but it still works just like any other join. And then concatenating the strings, filtering according to the facility name, and then removing duplicate rows, and finally ordering. Produce a list of costly bookings. So we want to see all bookings that occurred in this particular day, and we want to see how much they cost the member, and we want to keep the bookings that cost more than $30. So clearly in this case we also need the information from all tables, because if you look at the expected results, we want the name of the member, which is in the members table, the name of the facility, which is in the facilities table, and the cost for which we will need the bookings table. So we need to start with a join of these 3 tables, and since we did it already in the last exercise, I have copied the code for that join. So if you want more detail on this, go and check the last exercise, as well as I have copied the code to get the first name of the member by concatenating strings and the name of the facility. Now we need to calculate the cost of each booking. So how does it work looking at our data? So we have here a list of bookings, and a booking is defined as a number of slots, and a slot is a 30-minute usage of that facility. And then we also have MEMID, which tells us whether the member is a guest or not. I mean, whether the person is a guest or a member. Because if MID is 0, then that person is a guest, otherwise that person is a member. And then I also know the facility that this person booked. And if I go and look at the facility, it has 2 different prices, right? One price is for members, the other price is for guests, and the price applies to the slots. So we have all of the ingredients that we need for the cost in our join, right? And to convince ourselves of that, let us actually select them here. So in booking, I can see facility ID, member ID, and then slots. And then in facility, I can see the member cost, the guest cost, and I guess that's all I need really to calculate the cost. And as you can see, after the join, I'm in a really good position because for each row, I do have all of these values placed on each row. So now I just have to figure out how to combine all of these values in order to get the cost. Now, the way that I can get the cost is that I can look at the number of slots, and then I need to multiply this by the right cost, which is either member cost or guest cost. And how do I know which of these to pick? It depends on the MEMID. If the MEMID is 0, then I will use the guest cost. Otherwise, I will use the member cost. So let me go back to my code here. And after this, I can say, I want to take the slots and I want to multiply it by either member cost or guest cost. Now, how can I put some logic in here that will choose either member cost or guest cost based on the ID of this person? What can I use in order to make this choice? Whenever I have such a choice to make, I need to use a case statement. So I can start with the case statement here, and I will already write the end of it so that I don't forget it. And then in the case statement, what do I need to check for? I need to check that the member ID is 0. In that case, I will use the guest cost. And in all other cases, I will use the member cost. So I'm taking slots and then I'm using this case when to decide by which column I'm going to multiply it. And this is actually my cost. Now let's take a look at this. And so I get this error that the column reference MEMID is ambiguous. So can you figure out why I got this error? What's happening is that I have joined multiple tables and the MEMID column appears twice now in my join. And so I cannot refer to it just by name because SQL doesn't know which column I want. So I have to reference the parent of the column every time I use it. So here I will say that it comes from the bookings table. And now I get my result. So if I see here, then I can see that I have successfully calculated my cost. And let's look at the first row. First, it's the mem ID is not 0, therefore it's a member. And here the member cost is 0, meaning that this facility is free for members. So regardless of the slots, the cost will be 0. And let's look at one who is a guest. So this one is clearly a guest, and they have taken one slot, and the member cost is 0, but so it's free for members, but it costs 5 per slot for guests. So the total cost is 5. So based on this sanity check, the cost looks good. Now I need to actually filter my table because we have we should consider only bookings that occurred in a certain day. So after creating my new table and joining, I can write a where filter to drop the rows that I don't need. And I can say this is the time column that I'm interested in. The start time needs to be equal to this date over here. And we have seen before that this will not work because start time is a timestamp. It also shows hour, minute and seconds, whereas here is just a date. So this comparison will fail. And so before I do the comparison, I need to take this and reduce it to a date so that I'm comparing apples to apples on the time. Check that that didn't break anything. Now we should have significantly fewer rows. So now what we need to do is to only keep rows that have a cost which is higher than 30. So can I go here and say and cost bigger than 30? No, I cannot do it. Column cost does not exist, right? Typical mistake, but if you look at the logical order of SQL operations, first you have the sourcing of the data, then you have the where filter, and then all of the logic by which we calculate the cost happens here, and the label cost happens here as well. So we cannot filter on this column, on the column cost, because the where component has no idea about the column cost. So this will not work. But what we can do is to take all of the logic we've done until now and wrap it in round brackets, and then introduce a common table expression and call this T1. So I will say with T1 as, and then I can from T1, and now I can use my filter, right? So cost bigger than 30, I can select star from this table, and I'm starting to get somewhere because the cost has been successfully filtered. Now I have a lot of columns that I don't want in my final result that I use to help me reason about the cost. So I want to keep member, and I want to keep the facility, but I don't want to keep any of these. Great. Now, as a final step, I need to order by cost descending, and there's actually a issue that I have because I copy pasted code from the previous exercise. I kept a distinct, and you have to be very careful with this, especially if you copy paste code. Anyway, for learning, it would be best to write it always from scratch. But the distinct will remove rows that are duplicate and can actually cause an issue. Now I remove the distinct and I get the solution that I want. And if you look here, we have, if you look at the last two rows, you can see that they're absolutely identical. And so the distinct would remove them. But there are two bookings that happen to be just the same in our data. And we want to keep them, we don't want to delete them. So having distinct was a mistake in this case. To summarize what we did here, first we joined all the tables so we could have all the columns that we needed side by side. And then we filtered on the date, pretty straightforward. And then we took the first name and surname and concatenated them together, as well as the facility name. And then we computed the cost. And to compute the cost, we got the number of slots, and we used a case when to multiply this by either the guest cost or the member cost according to the member's ID. And at the end, we wrapped everything in a common table expression so that we could filter on this newly computed value of cost and keep only those bookings that had a cost higher than 30. Now, I am aware that the question said not to use any subqueries. Technically, I didn't because this is a common table expression. But if you look at the author solution, it is slightly different than ours. So here they did basically the same thing that we did to compute the cost, except that in the case when they inserted the whole expression, which is fine, works just the same. The difference is that in this case, they added a lot of logic in the where filter so that they could use a where filter in the first query. So clearly they didn't use any columns that were added at the stage of the select. They didn't use cost, for example, because like we said, that wouldn't be possible. So what they did is that they added the date filter over here. And then in this case, they added a logical expression. And in this logical expression, either one of these two needed to be true for us to keep the row. Either the memID is 0, meaning that it's a guest, and so the calculation based on guest cost ends up being bigger than 30. Or the memID is not 0, which means it's a member, and then this calculation based on the member cost ends up being bigger than 30. So this works. I personally think that there's quite some repetition of the cost calculation, both by putting it in the where filter and by putting it inside the case when. And so I think that the solution we have here is a bit cleaner because we're only calculating cost once in this case, and then we're simply referencing it thanks to the common table expression. So if you look at the mental models course, you will see that I warmly recommend not repeating logic in the code and using common table expressions as often as possible, because I think that they made the code clearer and simpler to understand. Produce a list of all members and their recommender without any joins. Now we have already solved this problem, and we have solved it with a self join. As you remember, we take the members table and join it on itself so that we can get this recommended by ID and plug it into members ID, and then see the names of both the member and their recommender side by side. But here we are challenged to do it without a join. So let us go to the members table and let us select the first name and the surname. Now we actually want to concatenate these two into a single string and call this member. Now, how can we get data about the recommender without a self join? Typically, when you have to combine data, you always have a choice between a join and a subquery, right? So what we can do is to have a subquery here, which looks at the recommended by ID from this table and goes back to the members table and gets the data that we need. So let's see how that would look. Let us give an alias to this table and call it mems. And now we need to go back to this table inside the subquery, and we can call it recs. And we want to select again the first name and surname like we're doing here. And how are we able to identify the right row inside this subquery? We can use a where filter, and we want the recs memID to be equal to the mems recommended by value. And once we get this value, we can call this recommender. And now we want to avoid duplicates. So after our outer select, we can say distinct, which will remove any duplicates from the result. And then we want to sort, I guess, by member and recommender. And here we get our result. So replacing a join with a subquery. So we go row by row in members, and then we take the recommended by ID, and then we query the members table again inside the subquery, and we use the where filter to plug in that recommended by and find the row where the memID is equal to it. And then getting first name and surname, we get the data about the recommender. And that's how we can do it. In the mental models course, we discuss the subqueries, and in this particular case, we talk about a correlated subquery. Why is this a correlated subquery? Because you can imagine that the query that is in here, it runs again for every row. Because for every row, I have a different value of recommended by, and I need to plug this value into the members table to get the data about the recommender. So this is a correlated subquery because it runs every time, and it is different for every row of the members table. Produce a list of costly bookings using a subquery. So this is the exact exercise that we did before, and as you will remember, we actually ignored the instructions a bit, and we did use not a subquery but a common table expression, and by reference this is the code that we used, and this code works with that exercise as well, and we get the result. So you can go back to that exercise to see the logic behind this code and why this works. And if we look at the author's solution, They are actually using a subquery instead of a common table expression. So they have an outer query, which is select member facility cost from, and then instead of the from, instead of telling the name of the table, they have all of this logic here in this subquery, which they call bookings. And finally, they add a filter and order. Now, this is technically correct, it works, but I'm not a fan of writing queries like this. I prefer writing them like this as a common table expression, and I explain this in detail in my mental models course. The reason I prefer this is because it doesn't break queries apart. So in my case, this is one query and this is another query, and it's pretty easy and simple to read. However, in this case, you will start reading this query and then it is broken in two by another query. And when people do this, sometimes they go even further, and here when you have the from, instead of a table, you have yet another subquery. It gets really complicated. So because of these two approaches are equivalent, I definitely recommend going for a common table expression every time and avoiding subqueries unless they are really compact and you can fit them in one row. Let us now get started with aggregation exercises, and the first problem, count the number of facilities. So I can go to the facilities table, and then when I want to count the number of rows in a table, and here every row is a facility, I can use the count star aggregation and we get the count of facilities. So what we see here is a global aggregation, and when you run an aggregation without having done any grouping, it runs on the whole table. Therefore, it will take all the rows of this table, no matter how many, compress them into one number, which is determined by the aggregation function. In this case, we have a count, and it returns a total of 9 rows. So in our map, aggregation happens right here. So we sourced the table, we filtered it if needed, and then we might do a grouping, which we didn't do in this case. But whether we do it or not, aggregations happen here. And if grouping didn't happen, the aggregations at the level of the whole table. Count the number of expensive facilities. This is similar to the previous exercise. We can go to the facilities table, but here we can add a filtering because we're only interested in facilities that have guest cost greater than or equal to 10. And now once again, I can get my aggregation count star to count the number of rows of this resulting table. Looking again at our map, why does this work? Because with the from, we're sourcing the table, and immediately after the where runs and it drops unneeded rows. And then we can decide whether to group by or not, and in this case, we're not doing it. But then the aggregations run. So by the time the aggregations run, I've already dropped the rows in the where. And this is why in this case, after dropping some rows, the aggregation only sees 6 rows, which is what we want. Count the number of recommendations each member makes. So in the members table, we have a field which is recommended by, and here is the ID of the member who recommended the member that this row is about. So now we want to get all these recommended by values and count how many times they appear. So I can go to my members table, and what I need to do here is to group by recommended by. So what this will do is that it will take all the unique values of this column recommended by, and then it will allow me to do an aggregation on all of the rows in which those values occur. So now I can go here to select and call this column again. And if I run this query, I get all the unique values of recommended by without any repetitions. And now I can run an aggregation like count star. What this will do is that for recommended by value 11, it will run this aggregation on all the rows in which recommended by is 11. And the aggregation in this case is count star, which means that it will return the number of rows in which 11 appears, which in the result happens to be 1. And so on for all the values. What I also want to do is to order by recommended by to match the expected results. Now what we get here is almost correct. We see all the unique values of this column and we see the number of times that it appears in our data. But there's one discrepancy, which is this last row over here. So in this last row, you cannot see anything, which means that it's a null value. So it's a value that represents absence of data. And why does this occur? If you look at the original recommended by column, there is a bunch of null values in this column because there's a bunch of members that have null in recommended by. So maybe we don't know who recommended them, or maybe they weren't recommended, they just applied independently. When you group by, you take all the unique values of the recommended by column, and that includes the null value. The null value defines a group of its own. And the count works as expected because we can see that there are 9 members for whom we don't have the recommended by value. But the solution does not want to see this because we only want to see the number of recommendations each member has made. So we actually need to drop this row. Therefore, how can I drop this row? Well, it's as simple as going to after the from and putting a simple filter and saying recommended by is not null. And this will drop all of the rows in which that value is null, therefore it won't appear in the grouping, and now our results are correct. Remember, when you're checking whether a value is null or not, you need to use the is null or is not null. You cannot actually do equal or not equal because null is not an actual value. It's just a notation for the absence of a value. So you cannot say that something is equal or not equal to null. You have to say that it is not null. Let's list the total slots booked per facility. Now, first question, where is the information that I need? The number of slots booked is in the CD bookings, and there I also have the facility ID, so I can work with that table. And now, how can I get the total slots for each facility? I can group by facility ID, and then I can select that facility ID. And within each unique facility ID, what type of aggregation might I want to do? In every booking, we have a certain number of slots, right? And so we want to find all the bookings for a certain facility ID and then sum all the slots that are being booked. So I can write sum of slots over here. And then I want to name this column total slots, looking at the expected results, but this will actually not work because it's two separate words. So I actually need to use quotes for this. And remember, I have to use double quotes because it's a column name. So it's always double quotes for the column name and single quotes for pieces of text. And finally, I need to order by facility ID. And I get the results. So for facility ID 0, we looked at all the rows where facility ID was 0, and we squished all of this to a single value, which is the unique facility ID. And then we looked at all the slots that were occurring in these rows, and then we compressed them, we squished them to a single value as well, using the sum aggregation, so summing them all up, and then we get the sum of the total slots. List the total slots booked per facility in a given month. So this is similar to the previous problem. except that we are now isolating a specific time period. And so let's just think about how we can select bookings that happened in the month of September 2012. Now we can go to the bookings table and select the start time column. And to help our exercise, I will order by start time descending, and I will limit our results to 20. And you can see here that start time is a timestamp column, and it goes down to the second because we have year, month, day, hour, minutes, second. So how can we check whether any of these dates corresponds to September 2012? We could add a logical check here. We could say that start time needs to be greater than or equal to 2012 September 1st, and it needs to be strictly smaller than 2012 October 1st. And this will actually work. As an alternative, there is a nice function that we could use, which is the following: date trunc month start time. Let's see what that looks like. So what do you think this function does? Like the name suggests, it truncates the date to a specific granularity that we choose here. And so all of the months are reduced to the very first moment of the month in which they occur. So it is sort of cutting that date and removing some information.